inside the podium because I like to stroll around, but today I'm going to be present here. I'm going to lecture you for some reason. I don't know. So excuse me for that. And I see many faces that been to my talk about C++20 last day, like yesterday. And I said that it's a good time. Everybody already using C++20, but then I showed you that only 48% of people are just using C++20. It's already almost 2026, and C++23 is stable. So you can already start moving to C++23. And as you've seen there, only 26% of people are using C++23. So with each C++ version, it's a struggle. It's really hard for people to start moving. But I really think if you haven't moved to C++20 right now, it's really better to push towards C++23. If you are not using automotive stuff and things that need MISRA rules, you can really move forward faster. And I think even with MISRA, we need to push it forward to make it a little bit better with the standardization, because postmodern C++ is much better and much safer. You cannot stay with C++17 in the year 2026. That's my opinion, and I really think you will enjoy it. Yesterday, I told you that I will show less than 50% of what we got in C++20. Today, I'm going to show almost everything that we got in C++2023. The changes are smaller. So that doesn't work without being connected. So a few words about myself. I am Dathskovsky. I have more than 20 years now of experience in system programming. I work in a company called CiraDB that develops blazing fast databases. If you need zero latency, this is the best database for you. The C++ code there is amazing. We are actually using already C++26 for some things, and we are pushing forward all the time. All the new compilers, everything needs to be the newest and the best. I have a LinkedIn where I talk about C++ and other things, so you can catch me up there. I also have my own blog post where I talk about C++, where I can speak about the things that I'm writing on LinkedIn in a better way, in a larger amount of words, let's call it that. And I have a YouTube channel. So the YouTube channel, I have 14 videos. I really try to make video once a month, but sometimes you don't have the time for that. As I mentioned, this is really funny for me. Like just yesterday, I showed C++20 aperitif, let's call it that, because I just show a couple of things. That's what you can do. Here's what you have. And today we're going to speak about C++23. So that's really weird. Like, it never happened before. Yesterday when I started, I said, what can you expect? And I promised there will not be any assembly, there will not be crazy templated code, there will not be things that are hard to understand. But today I cannot promise that, because C++23 is really about performance and really about asynchronously. So you have coroutines, you have better way to create coroutines. And as you can see here, the Android is looking at threads that are running, and inside each thread there are 2 threads. So basically inside each one of the threads you have coroutines. And all the language is about, and all C++23 features are around those things. Of course, not only asynchronous things, we have performance things as well. So to understand performance, I will have to show you assembly, but don't worry, I will explain everything into details. Let's start with the language features. So, feature testing. I know, and people that are watching me on YouTube, and people here, I know that it was a feature from C++20. But the sheer number of macros that are made for feature testing that was added in C++23 is worth mentioning. And I couldn't squeeze it into C++20 because I wanted to show more important things that were added there. So what are feature testing? Basically, those are macros that are predefined inside the compilers or the standard library that gives you the ability to understand what features do you have right now. In this example, I'm showing that we are using the C++ macro that just expands to a number. The number is pretty easy to understand. the first 4 numbers are the year. And the 2 numbers on the end, on the postfix, are basically the month when the release was done. So here we can see that we want to use C++20, not less than C++20, and the most basic version of it. If it's not C++20, then we are exploding. And yes, I know we always say that macros are evil and they shouldn't be used, and I'm showing you macros right now. But we have to understand, macros are still good for something. And for this, if you have a library features that you need to create, and you actually need to support number of different compilers and number of different departments in your company, where the library will work with C++20, or it will work with C++17, or somewhere you have C++23 features, it's really, really strong feature. So let's just be like the 3 monkeys, and we will see no evil, hear no evil, and enjoy the macros. So another thing that we can say, ask for is not just the whole C++ version. We can ask for a specific language feature. Here we are saying we need to support virtual polymorphism that I showed yesterday. So to support virtual polymorphism, const expression feature has to be 2019-07. That's where this feature was released. If we don't have it, probably we cannot do something, and then we need to fail. It extends to library features as well. So if you need something from the library and not from the language, all you need to do is to add the prefix of lib, cpp lib, const expression string. For this example, const expression string, it just means that I need the const expression constructor inside the string. And there are many, many, many macros that you need to know about. Again, if you are writing a library code, it's super helpful because it lets you understand exactly what features do you have and exactly what you can or cannot implement. So just take a picture of that and learn about everything there. Now let's continue. If we started with some evil macros, let's continue with evil macros that are really helpful. C++23, for a surprise, added a lot of things with macros. And here is an example of something that is really useful in my opinion. Let's say that you have a program, and your program has definitions that are provided by the build system. So in this example, you have 3 different definitions that you have to check for. Before C++23, you would look at this and you will have to write it in an arrow way. So we are checking for something else, then we are checking for something else, and then we need to do else, and then we're checking for something if something is not defined, and elsing and ifing, and it's an arrow and it's a U in my opinion, because arrow pattern is an anti-pattern, we shouldn't use it, but we had no other way to do that. And a lot of programs have even more than 3 things that they need to check. So think about it, it's just growing inside. With C++23, we got the simplest things they could have had long time ago. So we have else if def and else if not def. So instead of using an arrow pattern, we are just using a normal pattern and we are removing all the else clauses, and it looks much, much better in my opinion. Yes. So another feature that was added is warnings. Before C++23, we could just create an error. Here with C++23, we can warn. We can say, okay, something is missing or something is deprecated in our code, so the user should know that it's deprecated, and we shouldn't kill the program for that. So now we have the ability to do it with warnings. Multidimensional array access. So this is something that is really important, and it always was lacking in C++. Let's try to understand it a little bit better. So in this example, in C++, if we want to create a multidimensional array, we had to create an array of arrays of arrays. Here we have 3 dimensions, and that means we have an array of matrices, and inside it you have an array of arrays. So that's a little bit problematic in my opinion. It looks bad. And to access it, you need to give it all the dimensions in different bracket parentheses, sorry. So what happens when you're doing this? Let's say we have this A with 1, 2, 3, and we want to assign A to it. First, we peel off the first array, the array that contains all the matrices inside it. So the first operator returns a reference to the matrix. The second one returns a reference to an array, a one-dimensional array. And the third one will return the actual reference to the value that you want to assign. This has overheads. Instead of just returning the value, you're peeling the arrays, and you will have an overhead. Not always. Almost all compilers have a way to remove that overhead. But if something is not known, you may pay for that. And because of that, most of the library developers and people that needed three-dimensional array, four-dimensional array, if you're using tensors, they're always develop their own structs with the operator, with the call operator inside them. So the call operator here, we are just creating a struct that's called array3d that has an array with a dimension of sx, sy, sz, basically a one-dimensional array that is big enough to contain all the data that we need. And inside the call operator, we're just doing some mathematical stuff, skipping all the matrices, then skipping all the one-dimensional arrays, and then adding what is left to the z. So this is much better because it's easier to understand and you don't have the overhead. The compiler can deal with those multiplication operations and plus operation and addition operations in an easier way. But the problem here is, in my opinion, when you use it, it looks like a function. You are calling a function and setting something into the function. This looks kind of weird. And this looks weird because until C++23, the brackets operator or the access operator could accept only one parameter. So you couldn't use it at all. With C++23, we can finally use the bracket operator or the access operator and do the same thing as we did with the call operator, but just to do it correctly. So now when we are using it, we are using it like that. That is more understandable. You understand that you have a three-dimensional array, that you want to access it in this dimension, and you want to set a value inside it. Much, much more readable for the user, much, much better for everyone. It's better to understand and better to read and maintain the code afterwards. But still, it's lacking. So if I would define a regular array in C++23, it will not have this feature. I will still need to peel it. So I still need to create, my own structs. Who knows which language is this? It's one of my favorite languages. Anyone can guess? Oh, I wrote it! Oh my God. But you found it, good. So it's Pascal, it's one of my favorite languages. Basically, Pascal had this feature in 1970, when it just started. We had three-dimensional static array with boundaries that you could access in a normal way. Why didn't C go with this? Why did C do the overhead? So I have to say, with this one, Pascal is better. It's recorded. Oh. I won't get back to the community anytime soon. So it's really easy to use and it's fine. C++23 promised us something that's called MDspan. But look, MDspan is far, far away. It's far there and Android is crying and I'm crying because we will speak about it later. Static operators. So static operators is a cool thing that was added. Let's talk about this by showing an example. Here we have two classes. Test1, that is just a functor. It has the call operator that receives an integer. The second class has a static function that's called f, and that's it. To create a functor and to use a functor, we need to create the object. Then we have a function that calls a countIf with the object, with the functor object, and the other one calls the static function. Which one of those do you think will be more performant? Functor? Who is for functor? Who is for the static function? Right. And this is because when we have the member function or the operator, we have to create this. As you know, the first parameter for each member function is implicit this. And to create this implicit this and to push it through it, it takes more assembly operations. Here I'm showing assembly for RISC-V. Basically, you can see that for RISC-V, just to use the member function, you need to push R12 into the stack. Then you need to push RAX into the stack. This is basically the pointers. Then you're loading an effective address. This is basically moving this to the correct location. And then you need to move something else. You need to move another thing in. And basically, it's 4 more operations that are not wanted. Why do we need to pay for that? On the other side, when you're using the static function, you're not paying for those things. And the code is much, much easier, smaller, not easier. So in C++23, we got this ability. They said, why not to add static on an operator, on a call operator? So all we need to do is basically we are creating a functor and we are marking it as static. We are creating the functor object as we did before, and we are using it in a normal way. In my opinion, using those static functions are a little bit cluttered and less understandable. Here, because we did something with static and it's a functor, it's a clearer code and it's easier to read and maintain, in my opinion. And now when we will look at this, you can see that you don't have those operations anymore. You don't have these problems. You're actually not pushing anything, and you're calling a function that is a simple function that is an operator function inside the functor. Lambdas are getting better with each version. And in C++23, lambdas got better again. So you remember, we just added static to a functor object. Basically, lambdas are functor objects. Anonymous functor objects, but still functor objects. So we needed a way to do it on lambdas as well. And here's how we're doing it. It's basically adding the static after the parameter clause. Here we have just a lambda that we are adding static after the parameter clause, and that's it. If we will look at the disassembly or the assembly of this, and it's not an assembly, if you will look at what the compiler will create for it, you can just see that it adds static to the bool call operator, and that's it. All those things that are making a little bit better performance were added for MDspan, that we will talk later. Because MDspan is promising to be without overhead, almost without overhead. But to do all these things, C++23 moved around MDspan and created a better language with more performance, because we still don't have MDspan. Another thing that was added in lambdas is attributes. You can add attributes to your lambdas now. You have prefix attribute and a postfix attribute. So the prefix attribute is something that is adding an attribute on the operator itself. Here I'm saying no discard. That means that the value from the lambda cannot be discarded. The postfix attribute is something that doesn't work yet. Basically, if you would look at the paper that adds it, they're saying, we want to add alignment on those things. I have tried to add alignment on the attributes, and all the compilers are just saying, nah, that won't work. So maybe it's a problem with the compilers, maybe it will be fixed, but I would use alignment on a lambda. That sounds like a good idea. This one is a little bit tricky. So this one is called decaying copy or decaying auto-conversion. So what does it do? Let's look at this example. We have two functions here. Popback1 that is creating an A and then erasing the A from the vector. Popback2 is receiving a vector as well, but it's just pushing the R value into the erase function. So from this perspective, which function do you think will be more performant, 1 or 2? Who is for 1? 2? Very good. And this is why. We have 5 more assembler operations to do that. Why did it happen? Who thinks he knows?
Can you go back?
Local object.
But why the local object does that? Usually we have something that's called in C++ named return values, and we can move implicitly. Why didn't it happen here?
To allocate at the stack.
The problem is basically, it's almost that. The problem is that the expression to create an L value is just an expression to create a variable. The copy is a property of that expression. The property of that expression binds the expression to be something on the stack. So the compiler cannot do anything with it. You are basically telling him, hey, copy this here, and then use it. So you're extremely saying to him, copy this. But when we are not using that, and we are using our value reference inside the function, we don't need to do all the copying there. So that's really great. Another thing is, basically this auto-copy or auto-conversion is stating that we have a state where we want a PR value of something to be copied. PR value copy costs nothing, but it means that we are actually want a PR value here. Not R value, not a regular R value, not L value, just PR value. And it will always work. This is the best thing about it. It will always work for all types, even non-trivial types. You may say to yourself, we could do it before. We could just say, let's get the type from the back and wrap it with the type. But the problem is, I already kind of stated it. If the type is non-trivial, if it has no copy, we cannot do it here. But with the auto, it will always work. It will always push the PR value of what it needs, because the compiler knows what it needs to be, and it understands that it just needs to push it forward as a PR value. Another thing that this conversion added is helping with ambiguity. So C++ has a lot of ambiguous things to figure out, and this helps with it. Here we have a struct M that is defined before our struct, and we have a struct S. Inside struct S, we have a call operator that returns ourselves as a pointer, and we have integer that's called M. Now, integer that is called M we also have a struct that's called M. Then we have a function that's called call M that receives an S, and then we are using auto S, parenthesis, calling it, and using M. So what's the ambiguity here? The ambiguity here is before C++23, the compiler thought that we are creating a function. It says, oh, you are having a function that returns an auto type, receives an S, and then you are calling M. And it returns M because of the auto. And from C++23, you can use it. It understands that it's not an expression, that it is not a definition, it's an expression. We are just want to have a PR value of S, call a function operator on it, and return an M. And get an M, basically the member from inside the class. So it helps with ambiguity a lot. Literal types. So we all knew that we have a lot of literal types in C++ because it's easier to write. You could write U, L, UL, LL, and ULL, and it will just create the correct type for you, instead of you actually stating the full type and opening parentheses and pushing a value in. So it shortens the code. In C++23, we got 2 new types. So basically, UZ is the easiest type to understand because UZ is just size t. In this system, size t is unsigned long, but another system it can be anything else because size t is something that is portable. Z is, on the other hand, a little bit more complex. Z is a new POSIX type called signed size t. Most of the implementation give it -1 to all the numbers that we have. I actually really like it because you have an erroneous value for functions that return size t. Until now, you didn't have something that is erroneous, or you would use something like OXFFFFF or something like that. But now we can actually define something that's an actual error that returns from a function that returns something that is size t. Better implicit moves. So we already got to talk a little bit about implicit moves, but it got even better. We have more things about named value returns. So here's an example. We have a very bad function, and what is bad with it? Who can say what is bad here? We are returning reference to the temporary. So we are returning a reference to the temporary in y because we have created y on the stack. And we are returning a reference to a local value x because we pushed x as an r value, and it's only in the function. It resides only in the function. So no matter what we are doing here, we are returning dangling references. Until C++23, the compiler sat on it and did nothing. Nothing. You would go cry in the corner to try to find some problem in code like that because you added a reference for no reason, but the compiler wouldn't complain. It would just say, yeah, I can compile that. That's your problem. You know what you're doing, right? If you're writing C++, you're a big boy or a girl. But since C++23, we get normal errors. So you cannot do these problems anymore. And that makes your programs much, much safer. It helps you with debugging, and it helps you to write better code. And the error messages. I love the new error messages in C++. They're much shorter, and they're explained in normal English, unlike the previous errors. And even with templates, they are much, much better. What is the problem here? Who can say? And why is it the same? So, what's your name? David. The problem here is that we put s in parentheses. And because we have put s in parentheses, we're saying this is an expression. And because this is an expression, we are probably want to return a reference to that expression until C++23. So basically, in C++23, the return value rules became much, much simpler. And now with C++23, it removes the tedious process or the double process that was done for named value returns, and it just understands, hey, the thing tries to return a string with an R value. So please return an R value. I don't want an L value here, and it makes your program much, much better. Deduction by inheritance. Let's say that we have three classes. Class B is templated, and it has a constructor with the t-type. Class C inherits from class B, and it's templated on some type, and it exposes the constructor for class B. Class D is also inheriting from B, but it's not exposing the constructor for class B. If we will try to create D with just deduction guides, automatic deduction guides, we would expect it to work, but it cannot work because it gets a little bit confused. It doesn't know how B needs to be initiated. So if we will try to call it, we will get deduction guide failed. At least the error message that you will get is normal, and you can understand, oh, I'm missing something. But if you will do it with C, because we exposed the constructor for B, the deduction guide just knows that if we're creating a class with an integer that is inheriting from this class, and I have the constructor for it, I know how the construction works. And basically, when we are doing this, this is just fine. It understands that C is a C int. And this makes your code, again, a little bit more understandable and with less divergence. Let's call it divergence, because I would expect this thing to work even before C++23. Aliasing for statements. So for each statements got even better since C++20 when we got the ability to add values inside it. So we could do indexing, but now we can actually create types inside for loops. So why would I create a type for something that I need just for the for loop And this type will live on forever inside our code and will taint us with its presence. With C++23, you don't have to do it. Basically, it bounds your code very nicely. So if you need to use something just inside the for loop, you can create a type, you can create a value inside it, and just use it there. After the for loop is done, everything is gone. And in my opinion, it's a cleaner way and a more contained way, self-contained way. Self-contained programs are better. So this is a funny name, down with parentheses. Not my idea. The paper is called down with parentheses. And the paper is pretty simple, but it's pretty important. So you may know that lambdas, if the lambda doesn't have parameter list, you can drop the parentheses, right? So lambda 1 has the parentheses, but I can write lambda 2, which is exactly the same lambda, without the parentheses. The problem starts when you want to be something that is mutable. So here we have two maps, and we're creating lambda 1, which is, we are moving map number 1 to the lambda, and we need the lambda to be mutable now because we are changing the lambda state. So this is fine. But if you will try to remove the parentheses because you don't have any parameters in them, it will fail. Why? I don't know. No one knew. But now with C++23, we are done with the parentheses. And again, this makes your code with less divergence. You understand what will happen. I don't know what happened here and why the parentheses made such a fuss, but now we are rid of those. If const eval. So this is an important part. In C++20, we got away from the library to ask if we are running in a const evaluation zone or in a const evaluation code. To do that, we have to use a function called isConstantEvaluated. And if something is constant evaluated, then we have a simple const expression algorithm to use here. And if not, we have a very simple way to access a string. This is a toy example. You wouldn't do something like that. But what is the problem here? Anyone can say what's the problem in this function? The problem is that we are using ifConstExpr. So we are using ifConstExpr, and ifConstExpr pushes the if to work only in constant evaluation. So this will always say true. And again, the evil compilers did nothing. They just let you burn. Like you would write this code and it would just compile and everything would be fine. The only compiler that actually have done a good job with it, it's EDG. But maybe because EDG are in the committee and they're doing a lot of stuff there. So they did something right. Until today, I checked it before the talk and I checked it with all the compilers. If we are running with this, the compiler will say nothing. And so it's really, please stop using this function. If you have C++23, please don't use it. If you don't have C++23, just remove the const expression. With C++23, we got a fix for that. So it's not a library feature anymore. It's a language feature. We have the keyword const eval. So we had the if const expression. Now we can just ask if const eval. And it does exactly the same thing, and it will always do the right thing for you. If we are in const evaluation time, we will do something. If not, we will do something else. Basically, it removes and does a different templated code for const evaluation time and for non-const evaluation time. This is the best feature that we got in C++23, in my opinion. This fixed so many things, and it's just great. Self-deducing this may seem like a toy, but I will try to explain why is it very important. So what is self-deducing this? Just like in Python, we have the self argument that we need to push to the function. In C++, it was implicit, but we still got this. Here, in C++23, we are saying, okay, I want to specify myself. Please don't do it implicitly. So to do that, all you need to do is just to add this to the expression, self-deduction example, and call your parameter with a name, because you need to use this. The most important thing to remember when you're doing this, you don't have this inside your function anymore. It's not provided to you. So you have to use self. Now, even in this simple example, I think it's already much better because you are using a reference and not a pointer. So it's more C++-like to do something like that. But what else is it good for? Just to use a reference inside a function, it's not enough. We need more than that. We need to understand why this thing was created. And I will ask again, I asked yesterday, who likes boilerplate code? People actually like boilerplate code yesterday. So anyone here likes boilerplate? No, cool. So the first thing that this thing does is removes tons of boilerplate code, just like spaceship operator in C++20. Let's look at an example here. We have a class that's called value, and it's templated, and we have a has value and a t value inside it. It's just a basic wrapper. But the thing is that I want to return the value exactly the same way of the class's state. So if I'm L value, I want to return a reference. If I'm const and L value, I want to return const reference, etc., and so on and so on and so forth. And think about it. It's just one function. Look how much code we had to write. And the implementation inside the code itself is absolutely the same. It's total boilerplate that we don't need. So here comes self-deducing this for our help, and we can remove all the boilerplate code. Here we're saying that instead of using get as a regular function, we're templating it on self. We're returning a universal reference, and we're getting this self as universal reference as well. So inside the function, we will always get the object in the way that it was used. If someone used it as R value, this will be R value. If something used it at const L value, it will be const L value. It's always the same. And we're doing almost the same thing. The only important thing here is that we are forwarding self as the self that we received for the universal reference. So we want it to be exactly in the same state. And we removed all the boilerplate code. So we have just the code that we needed, and it works for all the statements that you need. Another good thing that self-deducing this is removing CRTP. So CRTP is a curious recurrent template pattern, thank you. It's a recurrent template pattern that it's not that hard, but for some reason people have a hard time with it. So how does it look? Here we have a base class, base templated class, that is templated on something, and this base templated class provides us a not equal operator. The not equal operator receives this as a reference, and then we have to extract this basically to convert ourselves to the disk that we are using, and then we are just using operator less. But that means that this, the thing that we are templated on, must have this operator inside it. And in line 172, this is the actual recurrent thing that we are seeing here. We have a dumbbell that is publicly inheriting from not same, and then we are providing dumbbell to the not same. So we are providing ourselves to something that we inherit from. Of course, we need to provide the operator less than, and that's as easy as that. To use it, we are creating two dumbbells, and then we can just use on the dumbbells, we can use not equal, something that dumbbell did not provide, but because it inherits from something that provides this, this works. Kind of weird. So with self-deducing this, we can remove this. We don't need CRTP anymore. Instead of using a templated class, we have a templated function. The templated function is basically saving us the conversion to self as well, because it's templated on the dumbbell. So we're providing ourselves, and we're using self-deducing this with universal reference, and we are providing another self as a universal reference, and then we're just using the less than operator that is provided by the dumbbell And in dumbbell, you don't have the recurrent pattern anymore. You're just inheriting from not same. And that's it. It's much simpler, in my opinion. It's much readable for newer people. It's just a template function now, instead of some weird pattern that people don't understand. This is another cool thing. So until C++23, if you wanted to create a recursive Lambda, you couldn't, because you have no way to access the object itself from the Lambda. Because now in C++23 we can provide ourselves into the function, we can actually use it. So we are providing ourselves as a parameter into the Lambda, and we are using it. And this is, again, this is great. This is just toy examples for Fibonacci and for factorial. But we can do something better. We can do recursive function to traverse a tree. Let's say that we have a function that needs to traverse a tree to balance a tree, for example, but we don't use it in anywhere else. So why do we need to create an actual function for it? Why can't it be a Lambda? And here is a great example for that, exactly. If we want to traverse a tree, please provide a tree, create a Lambda. This Lambda is used only in one function. That's it. Easy as that. This is an important thing that self-deducing this does for us. This is not boilerplating. This is not a thing that is just nicer to write or gives us more abilities for writing code. This is actual performance. So what is the problem here? I'm creating a small class with two parameters and one function that receives one parameter. I'm creating the class on the stack, and then I'm calling the member function. Why is it problematic? Why do you think it's problematic? Who can guess? Yes? Sorry? Not at the reference, it's worse than that. So the problem is, but it's a really good guess. The problem is that because we're creating the class on the stack, and because the implicit parameter this is a pointer, a reference basically, it needs to reside somewhere. So because it needs to reside somewhere, we're actually allocating it on the stack before and then passing it to the function. Why? Why do we need to do that? That's just not performant enough. And usually we don't need to do that for functions like that. So to fix it, all we need to do is to provide ourselves as a value. And if it's a small class, it's really good for performance. We are saying we are providing ourselves as a value here, and we are providing the parameter z that we wanted to multiply with. And then when we use it, we are using it in the same way. But if we will look at the disassembly, ta-da, all the allocation of the class is gone. And because we are provided ourselves to inside, all we had to do is to allocate, to basically provide the two numbers that were the members. That's it. As easy as that. Yes?
How does that work when the member function is not const? Does it then move the value back?
It doesn't need to move the value back. It just mutates it. So you are providing something that you cannot. It's an R value. So if you are mutating yourself, you cannot do that. This is a very important and not easy thing to understand. So we have something that's called Lambda fiasco. Lambda fiasco with coroutines. And self-deducing this is fixing it. What's the problem? Like lambdas, coroutines have closure. They need to capture things into the coroutine. So to capture those things into the coroutine, basically, to simplify it, the coroutine, when it captures the lambda, it creates a free function from it. And then it provides the lambda as a parameter. The problem here is that the lambda needs to be created somewhere in some scope, and then it's provided as a parameter, as a reference to this free function, and that means trouble. So if we will use code like this, and we will create a coroutine function, and we will move a unique pointer inside it, and we will do co-await and then co-return, that means when the co-return is called, we might not have x anymore because the lambda has disappeared from the stack. And this is the fiasco. If you are creating lambdas that captures parameters into it, that has a closure, that's a problem. How do we fix it? The fix is pretty simple. We're using this, self-deducing this, as a value. So we are providing, instead of providing ourselves as a reference, if we will do this simple thing, just use this out of self, the function will still be a free function, but now we are saying to the compiler, hey, you cannot use references. I need this to live forever until I'm not finished. Because of that, the function scope is the one that's managing the lambda itself. We copied the lambda there, and until the function will not be done, it will not be done. It will have everything that it needs, and it saves a lot. Like we are using in Scylla, we are using a lot of coroutines, and it was always a problem because we had to create an actual function. I think you already understand that I don't like creating functions just to create functions, and we could create lambdas for that. And we just couldn't do it because of that. Because some lambdas had to have closure. And this just fixed everything. Since we're using C++23, the fiasco is gone. And it's much easier to write coroutine code. So as you can see, self-deducing this is good. It really helps you a lot. It helps you with the code. It helps you with how you're coding things. It gives you the will. Like C++ does it a lot. It gives the programmer the will and says, come on, you can do better things. And if you understand those things, you can actually do much better things, much performant things, and safer things, as you can see here. That's 99% of all features that were added into the language. Now we will talk about some of the features that were added into the library. And there were some features that were added there. So forward-like. Forward-like is an interesting specimen. We all know that C++ had forward. Forward just says, I want to forward something just the same way that I got it in the templated function. Forward light says something similar, but instead of forwarding the parameter, you're forwarding a parameter by the state of the class. So here you're saying, we have a callback that gets a function, a message, and a scheduler. And here we are saying, I want to submit something to the scheduler, but the parameter of the message needs to be in the same state of the lambda. So if the lambda is L value, I want it as an L value. If it's an R value, I want it as an R value. And this is basically forward-like was the first thing that was implemented in the library for self-deducing this. Without self-deducing this wouldn't be, we couldn't implement it. And it's used for calling the callback in two different ways. So we can call the callback in retry mode. We can call it again and again and again because it's L value. Or we can do a move on it, and then it's a R value, and that means that we are calling it once and failing. If it fails, it fails. There are many, many more things that you can learn from the paper, and I think it's really worth looking at it. This example I just took from the paper, but they have many more. Generators. So I really like Python, and I want to write in C++ as if it's Python. Like, why not? And I really want to write like that. I want to create auto, two parameters I and v, and there's a great function in Python that enumerates on all the containers. The enumeration just gives you the index and the value, and that's great. I can just use it for anything I want. And hooray, in C++20, we got coroutines and we can implement it. Let's see what it takes to implement something like that in C++20. So we are starting with a class. So far, so good. Inside the class, we're doing another class that's called promise type. The promise, of course, is important because you need to understand when you are doing core weight or core yield, you're returning a promise. And you're always switching between the promises. So we're implemented the promise here. Just 10 lines of code, nothing much. Then we need to create the handle. Then we need to create all the operation on the generator because we need to move it around because the generator is something that is returned by a coroutine. So everything moves around. And we are not done because we want it to be an iterated. So we have to create an iterator. So we're writing our own iterator now that uses a coroutine, that uses the handle, and removes everything, and adds, and moves it around. And we are not done yet. We have the iterator begin and the iterator end. And here we have the private age. And I don't know about you, but for simple functionality as that, I don't want to write almost 200 lines of code. That's a lot of code written for something that is very simple. And I said it a couple of times, C++ 20 coroutines makes me sad. It's so hard on the users. It's so hard on people that don't understand how to write them. And if you are not writing them daily, you just don't understand how they work. In C++ 23, it's got much, much better. It's easier because we have the generator type. So here you can see the same example, exactly the same example with the generator type. The generator is templated on a tuple of 2 integers. We have a function that's called enumerate. We have an index inside it. We have a for loop that iterates on everything and co-yielding with the index plus plus and v. That's it. 200 lines of code became 5 lines of code. This is amazing. Of course, one of the best things that we got in C++ 23 is that we finally have print. We don't need to use FMT anymore. We don't need external libraries. So it makes my life much, much easier. I like FMT library, but if I have it in the standard, I don't need to use it anymore. And that happens because Vitali is part of the standard and it's pushing it a lot. So another good function that we don't even have in FMT is print line. That means you have to be less expressive on the lines that you are printing. You don't need to put the /n after the line ends. It will do it for you. So it's just easier for the users. Better error handling. So this is great. C++ 23 has an error handling class called expected. Instead of throwing exception, you can use expected. That will be pushed around and moved around. And it's nice because it's monadic. That means you can do the operations on the same line and you're just saying what you want to do. So here's an example. We have an enum class that defines a problem, an error value. We have a function that processes an error. All it does is just prints it and then returns something that is unexpected. We're pushing it forward. And it returns an expected of an int and an error value. That's basically what we want to return and push forward all the time. Another thing that we have here is the process value. So if something is good, we still need to process the value. And here we're returning the same expected thing. We're printing it and returning 0 forward. So someone else in the monadic operation will use the 0 after us. Then we have a scary function that all it does is basically checking if some function can be called with the parameters that it was provided. If not, it returns unexpected with the function not invoked. If everything is fine, it just invokes the function and returns the number. Here we have the function that we will use. It's just a function that receives 2 integers, a simple function, and returns the summary of those 2 integers. And then to use it, we're just invoking the function, and then we can use the monadic operation on them, like and then. And then means after the function finished, you can call the process value. If the function didn't finish correctly, you have the or else. So in line 363, or else will be called, and then won't be called at all. There are more monadic operations that we got in C++ 23, and the optional that we already know since C++ 17 now has monadic operations as well. So basically it's pretty easy to use because they're almost the same. Instead of using the return values for the expected, I will just return an optional. And we have the same functionality here. And then we're using it exactly the same. But we don't have the error value, we just have optional none. So the usage is almost the same. I think it's really great and worth looking to if you have C++ 23. It's also gave us an ability to put a better detective head. So basically, Last time in C++20, I told you that we got better logging. In C++23, we got stack trace. So stack trace is great because stack trace is something that gives you the ability to look at the stack trace and investigate it. What's great about this, that it opens a lot of options for you. Think about it. You can write outside the applications that will investigate your core dumps for you. And you can do it because you are actually investigating each thing and you can understand from the stack trace what's going on. That's how it looks if you just print it. Another thing that you can do is better exception propagation. So when exception is called, you always know that something is wrong here, but you don't have the correct stack trace. With this thing, you can create an exception where you put the stack trace into the exception, you actually push it in, and then when the exception is actually called, you know what the stack trace was, and you can understand from where the exception was thrown correctly. In CPPCon this year, Eric Strauss had a great talk about how to make it even better. He went with this very, very far, and he explains how to do it, how to enter into to make it even better with entering lib unwind and changing some things, and then you have a couple of stack traces that you can use. So the talk is very, very good. I really say that you should look at it when you have the time. Cache friendliness. So cache friendliness is nice. We actually had a talk here by Jonathan this week about cache friendly algorithms. But C++23 gives us a little bit of cache friendliness with flat map and flat set. So the thing is, it's really easy. It's sometimes using something that is flat in memory gives you more performance. So you tend to think that O of 1 is better, but it's the biggest lie in computer science. You need to understand how your processor works and what you have. If you have something inside the cache and you have locality, usually doing a binary search, it's much, much faster than having an O1 algorithm like an ordered map. And now let's get back to MDspan. So it's 2026, and it's sad we don't have MDspan. None of the compilers have implemented it yet. And that's pretty bad because it's one of the, I think it's one of the best features that C++23 offered. And to show you what exactly do I mean, I will do it with an example of a kernel. So to do image processing, you need to process a kernel with convolution. And to do a convolution function in C++ without MDspan, it's tedious. It's doable, but it's tedious. With MDspan, we can do something like that. We just need to create all the types that we need. We have the span and the subspans, and we're creating the sizes. We have padded spans, because when you're moving a kernel on the window, you need to get outside. So we need to pad the first row with zeros and the last column with zeros as well to get the right filter. Afterwards, we have a do on span. So we are just creating a function that receives two MDspans, one MDspan and one function. We are saying that this function only works with MDspans that have 2 dimensions. And then we're looping on the dimensions and calling a function with the value and the indexes. Then we have the convolution function itself, where we are just calling the do on span with a lambda, where we are creating the parameters, and we're calling the convolution implementation. And the convolution implementation is pretty easy itself. It receives a kernel and the image kernel, and it multiplies them for filtering and just returns the return value that will be set into the output image. So that's not a lot of code, 37 lines of code for something that can be generic. With that, I'm done for today. C++23 has more features and more things that we need to know about. And it really makes your code better. It really makes your code simpler without divergence and without those little problems that we've seen before. And really, if you can, push for C++23. It's 3 years in the making. It's 3 years. It's stable. Yes, we don't have MDspan, but everything else is much, much better. And if you want MDspan, you can get it as an external library that's called Kakos. Kakos library is basically where they implemented, and everything is being imported from there to the standard. So it's there, you can use it, but it's still not in the compilers themselves. Thank you. Questions?
We don't have time for questions. Thank you, Alex.